Hello and welcome to Luckymath. In this video I want to finally show you how you can calculate the derivative of an exponential function a to the power x. So we want to know what is dx of a to the power x, where the exponential function has to satisfy these conditions as always, and if you don't understand the conditions, go check out the video up there. By the end of this video, you should be able to answer the question, what is this question mark? And we're going to proceed as follows. We try and express a to the power x in a form where we actually know how to calculate the derivative. And we get started by looking at the following function. And I hope you're familiar with this function, namely exp of x, which is equal to e to the power x. This is the natural exponential function, and in the video up there I try to convince you that this is the most beautiful and the most useful exponential function out of all of them. And the main reason is that if you try and take the derivative of this function exp of x or e to the power x, then what you get back is simply the original function e to the power x. So the derivative has no effect on the exponential function, on the natural exponential function. So now we actually already know how to take the derivative of one exponential function, so that's a start. And you'll see that in this video I often refer to e to the power x as exp of x, only such that you see that this is actually a function of x. In a minute you'll see why, don't be confused. Okay, so in the next step, let's try and calculate not only the derivative of e to the power x, but the derivative of exp of c times x. And to do this, we're going to need the so-called chain rule to calculate derivatives. And this goes as follows. So if we have a function f of x that is of the form h of g of x, so if we have a function in a function, the same what we have here, a function in a function, then the derivative of such a function is given by, we first take the derivative of the inner function, which would be g of x. So we would take g prime of x and multiply it by the derivative of the outer function, which is h of g of x. So h prime of g of x. And here we don't change the inner function, so g of x stays exactly the same. So if we were to apply this rule on that function, what we get is that x would be h, so this would be the h function, and c times x would be the g of x function. So then, if we take the derivative of g of x, which is c times x, then this obviously gives you c, because the derivative of that is simply c. And if we take the derivative of h, then you know that the derivative of the exponential function e to the power x simply stays the same, so the derivative has no effect on h, and therefore we get back exp of c times x. And that's the derivative of this function. In the next step, and this is the crucial step, we try and express a to the power x such that we have a new base. So we try and change the base of such an exponential function so that now we have as a base e. And then you'll see it will be very easy to calculate this derivative. So let's try. If we have a to the power x then isn't this exactly the same as x of ln of a to the power x, where ln is the natural logarithm, so the log to base e? And the answer is yes, because if you apply both the exponential function and the logarithm to this base on a function, this doesn't have an effect on the function. So if you don't understand this, go check out the video up there. And now in the next step, what we can do is let's use the power rule for logarithms, and I have again a separate video up there. And this rule says that you can take the exponent in front of the logarithm. So let's do that. So we get exp of x times ln of a. And if you like, you can also rewrite this as e to the power x times ln of a. By the end of this video, you will notice that this is actually a way more useful and handy expression for a to the power x. And soon you won't express any exponential function anymore with the base a, but you rather use the base e. So let's see. So now we are actually at the point where we can calculate the derivative. Let's try. So d dx of a to the power x is equal, obviously, to, if we express a to the power x as x of x times ln of a, right? So we can also write this. Exactly the same. And now try and shift your eyeballs from here to here. And you see that if you substitute ln of a by c, or the other way around, that this is exactly the same expression as this. And therefore this has also the same derivative as this. And so what we get is that you simply take for c ln of a in this expression. So we get ln of a times exp of x times ln of a. And yes, ln of a is simply again a real constant because there's no argument in here and a is just some constant base. Alright, and we can rewrite this also as, if you like, as ln of a times e to the power x times ln of a. And this we can also write as ln of a times e to the power ln of a, and this to the power x. I hope you know this rule, that this is simply, if you have a to the power n times m, this is the same as a to the power n to the power m. Okay, and then we can again use that if you apply both the exponential function and the log to any variable, you will get back the variable. So what we get back is, and this is our final result, so here this would simply be a again, what we get is that this is equal to ln of a times a to the power x. And this here was our question mark up here. Oof, we're done. Okay, so that's really the reason why e to the power x times ln a is really a much nicer representation of that. Thanks for watching, rate the video. If you have any questions, write it in the comments, and see you soon again on Lucky Math.